from Night City Labs, who's going to be presenting on hierarchical integration of RL and cerebellar control.
Um, so this will be a small theory about the cerebellum. I started this a while ago because colleagues started Logic and showed Mar that were using kind of new thinking with model ML. This is better. Can you hear me? Yes. Okay. And then so it started as a model and theory of the cerebellum, and it's expanded a bit of a theory of adaptive control more generally. So introduce kind of a new adaptive controller, how it integrates with RL models in DeepRL, and ultimately also how it would be a model and theory of the cerebellar function. Since a few years, DeepRL finally managed to do more continuous control with difficult tasks, more naturalistic movements, which a few years ago was not really possible, but it's still quite unique. It's very data hungry, not very robust. And all these difficulties are things that the cerebellum is known to maybe help us in our naturalistic movement. So the idea is that maybe by developing universal adaptive controller, we could improve, not only improve this DeepRL artificial agents, but also would be a model of circular function. So there is these two sides to the project. And so one thing to start off is to differentiate them RL from control. So control in the sense of control theory or adaptive control. They are very similar, both have the same framework of this kind of action environmental observation loop. You have some controller and some reward. But instead of trying to find out how to merge them, so you have like nice papers like vibration effect, trying to see what they have in common in some settings. Because they have such similarities, I will work more on trying to differentiate them. Because even though paramols could do things like continuous control, which have all these scales from planning to fast control, I do think by separating them, this could be made much more data efficient, and this could maybe map better also different brain areas. And if you take these fields, they actually can be quite different. If you take the standard like pulse on RL or in control theory, they will have quite a small intersection actually. And what I will focus on in the main differences is here, if you see the reward here, can be quite general, right? Can be go, can be live, and it's all about learning this value function that we'll try to optimize. While in adaptive control, usually you try to consider a quadratic cost, which is basically a stability around a reference. So there is these two constraints here that constrain much more the adaptive controller, but makes much more sample efficient. So, and the trick here will be to keep both. And this reference here, then, which is a bit mysterious in a very complex world, would come then from the RL model. So that's kind of a quick summary of the solution. So you pick your favorite DeepRL model that has an encoder and then a policy, and you optimize some. The value could be a dreamer or some critic. What I need from here is a policy, a baseline policy that already does the task reasonably well, and an encoder to some task-related space. And then I will add a controller, better robustness. So first I learn a formal. So given this latent trajectory and the actions you took, learn by supervised learning just in a few milliseconds, let's say, those steps where you read. And then you fix that. So then you have a dynamics model, a word model, there are synonyms here. And now you learn the controller. What the controller will do, so the key kind of conceptual innovation is that you reinterpret these predictions here as targets. So that would be like that reference for data control. So while you're walking, and a very complex trajectory, so moving space, you will be constantly predicting where it will be like in 100 milliseconds. And that, for the controller, is a target. So you're not using it for rollouts or planning or MPC, you're just doing the average trajectory, and that becomes for the controller what you want. So where you expect to be for the controller is where you want. And how you optimize this is using the same loss. You still want to, now that your forward mode matches the observation, but now instead of changing the forward mode, you change the world to match it forward. So that's why you actually have a negative sign here when you do the backpropagation to your controller, because you're changing the world to match your prediction instead of the other way. But the loss is the same, you just have a negative sign here when you do the transfer from the derivative. You notice that the idea is that when you have some perturbation, this formula will be a bit wrong, that's why you deviate it. But you still use the same formula to do the gradient, so there is a bit of a circularity that you hope the formula is not that wrong, so you still have that your gradient is aligning of the how you change a bit your actions, how you change the state. So that should be reasonably well predicted in your formula. And then in the end, the idea is you just sum, but simple sum of the two policies. The idea is that here, this is basically for me the cerebellar or the rest of the brain, let's say, while this the cerebellum. This could be then very short time scales or temporal or spatial, while this can be everything else. Another way of seeing this is to decompose. So you can have a value function, you're here in this state, you take an action, you're here, but with some variability, and you consider that your baseline is quite good, so it's a kind of a local maxima. You do some Taylor expansion, basically have two terms, which is the average value, and consider this is what RL would be maximizing, while how much should deviate, that would reduce your value, and that would be what controls then minimize, because then you would lose value. So in a kind of cartoon like this, you still have RL maximizing value, and control will minimize the variability around where it predict to be a bit without knowing actually about that you're maximizing value. Just take the baseline as low. So again here, the same thing, and then so the RL will be more where you want to go, what you want, and the controller makes sure you do that with precision. And the next thing is that by mixing these two, you can have like this kind of controllability balance that you have in adaptive control and control theory, but then are you bound how much you lose of value? So you can kind of mix the theory now. And so here's a simple example. So the protocol that I do is that I learn the baseline model, I learn the forward model, then I add a perturbation, then I fix those models, and then I add a control. So suppose you're here, you want to go here, so this action is back to be here, but you see that something changed, your muscle got tired, or you decalibrate your drum to end up here. And then the controller will learn then to push here, so that your total action will be closer to where you expect. So this works well, that when you add a perturbation, the controller kind of reduces the deviation. So, and you can do this kind of perturbation for more, I'm not sure the videos are working here. They're supposed to be walking, but okay. And then you see one walking property, one looks a bit ataxic, so wobbly and a bit of tremor. So this will be the perturbations, and then you can study a bit the variability in behavior. So this kind of decomposes by variability into the goal-directed variability because of decisions and the lack of control. So it's an interesting kind of already model of ataxia, just the perturbation side. But then we're also here focusing on then adding the controller. So you have this kind of Mujoko avatars. You fixed here the baseline reward, the policy and form model, and then you add the perturbation, which is I add a perturbation to the activator. So they're strong or too weak compared to what you know. It's an unknown P. You just see that you're undershooting or overshooting, but that's what the formal can see, and that corrects very quickly in green here. While in gray would be without adaptation, and in blue would be RL. But RL model, in principle, has the facility to learn it and has the correct objective function, but it's just too slow. It has to update the formal, then update the value function for the formal, then update the policy. This is not sample efficient enough for this kind of fast corrections and adaptation. So you can see here the control prediction error that it goes down quite quickly. The RL also goes down, but this is not fast enough. And here's the overall results that you see also in green here. The controller, you see also when I take away the perturbation, see the kind of reversal error because it's still like adapted to the perturbation. And we can do also then non-stationary unknown perturbation like we do have in our bodies constantly, muscles or any control system. And this the control can keep track this quite well, and it even rather goes a bit over the baseline just by stabilizing the baseline model. It has a reward even without perturbation. And you can see that the reward cannot the RL. So these are the principles that guide the model that have this kind of primary policy, and that should be laws prioritized in the control automatically tries to make that happen. And then you do that through this kind of formal in the latent trajectory. I call this a kind of a reflexive world model. So it tries to automatically bring back to what you expected, and you do this in some value-related latent space. Because if you do it in an observation space, that's cannot control the whole world. So important to have this test-related space where you actually control things. And a nice summary of this model or theoretical kind of very concise view of this model is that it's related with controllability. So here in this topic, we had a lot about empowerment and skills, which is about the much information of your actions and the future state. So that's a measure of control of the environment. And here you can see what this model is doing as, again, controllability objective, much information of your main policy and the future states, but achieved through a second policy, so through the controller. And to finalize, how does it, I think it not only is a new, quite nice functional universal controller, but it does fit a lot of things we know about the cerebellum. That's, I mean, I came with it about because of the cerebellum, so I do see it, but coming back now to the cerebellum, it does seem to fit, for example, the basics, that it does motor coordination and stabilization. It is universal, so it fits the different strands of theory of the cerebellum, like Mars about learning and perceptron, but also about being an adaptive controller. And by being universal, it could, for example, work for cognitive control because it's can be about any kind of controller. So if you're controlling something within your brain, maybe your emotions, and this is stabilizing that, you will see this kind of stabilization effects. It also has a lot to say about the teaching signal because it's supervised, so you have more dense teaching signal. It does look a little bit like reward prediction error. That's, in my opinion, why you see this kind of similarities, though it's not the same. It's a control prediction error, but it's unsigned, and it is temporal like cumulative reward prediction error, but it's also not really the same. Because it inherits the representation and it's just correcting within that representation, you don't have to learn it. So there's no representation learning here. So you can do this system in a single forward model. So that would maybe explain why you don't have recurrency cerebellum, because you don't have to need some complex representation. It also has this trick because you need to change the world of the form model. You need this negative gradient, which is what you see in the cerebellar synaptic plasticity. You have this anti-headed plasticity experience, but it fits this idea that you're changing the world to your model. And lastly, you you need the formal, and then you have to compute also the inverse for the action in the gradient. So this kind of computation that you see in the cerebellum seems to be there in some kind of mixed way. Here you do need these kind of computations, even though the exact mapping to this the cerebellum is not done here. It requires more work. All right, I'd like to thank my community at the Shibari Foundation, Lisbon, the Beautiful Institute. I recommend everyone to visit. And then since I left, I started my own company now on AI research, basically replace myself before somebody else does it. And I will talk about it whoever wants. And thanks for the attention.